Fantastic. Thank you, everybody. Want to welcome you all to the September 2022 meeting for the Raleigh Astronomy Club. And I would like to welcome any first-time guests or new club members. So if you're here in the room with us, any guests or new members, please feel free to introduce yourself at the break after our speaker. And for any new members or guests that are in the Zoom meeting, feel free to kind of drop your name and chat and introduce yourself. So we ask you to please be respectful and hold your questions until the end of the presentation, unless Patrick wants to take them at a certain point in time. And also for the audience in the room tonight, go ahead and please wait to ask your questions until we actually pass the microphone to you. So we are doing a hybrid meeting, so it's being broadcast on Facebook as well on Zoom. So if you ask a question and you don't have the mic, then the people in the Zoom meeting can't hear you, can't hear the question. So, all right, Dana, if you can jump to the next slide. All right, so welcome. We'll jump after that one. And next slide. All right, so some upcoming events that we've got. So it's just a quick introduction or a quick summary. The imaging group is on the 15th of this month. Then we have the first Friday, although it's not first Friday, at our Three Bears, or at the Three Bear Acre location. That's on September 16th, the Friday. Next, we have an outreach event at the Willard. We need about 2 more telescopes. That's a fun event here in downtown Raleigh on September 21st. Next, we have RAC Ops, and that will be at our Big Woods location as well as Howell Woods. After that, we have another outreach event at White Deer Park. We need more volunteers. With or without a telescope. So even if you're new and don't know what you're doing, we always need helpers to kind of engage people on the lines and so forth. We'll have our first Friday event outreach. Don't know if we have a location on that yet, but that's October 7th. October 14th will be our next meeting, and our own Doug Lively is going to give a talk about astronomy at Glacier National Park. And then we have the next imaging meeting on the third Thursday, October 20th, followed by the Staunton River Star Party. This is not necessarily a Raleigh Astronomy Club event, but rather is a local star party. And I strongly urge and invite people to attend that. And then last in October, we have our Big Woods and Howell Woods RAC Ops. Okay, so I would like to introduce, one more slide. So after our meeting, we like to socialize and get to know folks in the club well. So come on out to Sammy's Tap and Grill for either a late dinner, dessert, or a drink. And we'll have this picture up later with the address later on in the meeting as well. So without any further ado, I want to introduce our speaker tonight, Dr. Patrick Treuthardt. Okay. Patrick is an astrophysicist whose research focuses on the shapes, structures, and underlying physical processes of galaxies. He also takes part in science communication and public outreach activities. Now I lost my place where I was talking. That increase access to astronomy and science in general. He is currently the assistant head of Astronomy and Astrophysics Research Lab here at the North Carolina Museum of Natural Sciences. And tonight's talk is about how our understanding of the Milky Way has changed. What is its origin and eventual fate? We'll discuss some of the historical science that has shaped our perception of the galaxy and our place in it. And we'll also discuss some of the more modern revelations that have given insight into our galaxy's past, present, and future. So without any further ado, pass it over to Patrick.
All right, thank you. All right, thanks everybody. Well, thanks for inviting me, first of all, and thanks for everybody on Zoom. Unfortunately, I can't see anybody on Zoom, so if you have questions or whatnot, hopefully the people in the room can pass those along. Yeah, so my name is Patrick Treuthardt. I am an astronomer here at the museum. I'm one of the 2. I study galaxies outside of our own galaxy. So this is kind of what I'm talking about today is kind of tangential to what I do, because studying the Milky Way is actually different and, in my opinion, more difficult than studying galaxies outside of the Milky Way. And so what I study is basically the shapes and structures that make up galaxies. And so we're going to talk a little bit about that and how we, basically throughout history, how we've come to kind of understand what our own galaxy really is. Again, I can't see anybody on Zoom, but how many people here have not seen the Milky Way? I'm going to do the opposite. Everybody's seen the Milky Way. That's fantastic. Okay, because usually when I ask that, a lot of people raise their hands that they have never seen the Milky Way. But yeah, so obviously in this group, people have seen it. And so the previous picture was really colorized, but I feel like these pictures are a little more representative of what the Milky Way colors actually look like. And you can see the colors actually tell you stuff about the Milky Way itself, about what's going on in the Milky Way. And so in these images, you can see you're basically looking at the central part of the Milky Way, and you can see that it looks kind of orangish yellow. And if you were able to see the rest of the band, which I'll show you in a minute, it actually looks bluer on the outer parts from that. And that actually tells you something about what's going on in our own galaxy. So for those who have never seen this, never seen anything like this, this is just a view of our own Milky Way throughout the night. Obviously, it's a little jumpy. Okay, it's not translating very well. Sorry about that. But yeah, you can see the Milky Way throughout the night. And you can see we're looking at the outer parts right now, and you can see it looks a little bluer. And then you're going to see the central part, and it's going to look a little more yellow. So we don't have to watch the entire thing, but just so you get an idea of what's going on there. Obviously, that's the Milky Way. That's our own galaxy. And then here's just a different view that I just find to be pretty awesome, where you have image stabilized with the ground, with the sky. So you get a different perspective, probably a more realistic perspective of what's going on. Okay, so if we're able to subtract out the ground and just look at the Milky Way itself, this is what it looks like. This is essentially an all-sky view of the Milky Way itself. And so let me just point out a few things here. So you can see, see if you can see the pointer. Yeah, you can. So you can see these two objects right here. Here's one here, here's one here, and then there's a little guy over here. So when you look out in the night sky with your naked eyes, everything that you see is essentially part of our own galaxy. Those little three guys that you see there are the only things that you can see with your naked eye that are not part of our own galaxy. So the two little blobs on the bottom right, those are the large and small Magellanic Clouds, and then that little guy on the left there, that's the Andromeda Galaxy. And those are the only things that you can see with your naked eye outside of our own galaxy. Everything else that you see in the night sky is part of our own galaxy. And so there's just a tremendous amount of stuff out there, right? So what you're looking at is essentially 200 billion stars. So everywhere you look, you're going to be seeing stars within our own galaxy. And we estimate there are about 200 billion stars within the Milky Way. So to give you a sense, and again, I'm sorry for those people on Zoom, or actually everybody, because it looks great on my computer. But it's not able to capture it so quickly. I'm sorry about that. But this is a great animation by James O'Donoghue. He makes these really great animations that kind of like show you scale and speed and things like that within the universe. And what this is showing you basically a speed of light as basically if you could have light race around the surface of the Earth. It's really fast. Okay, obviously the speed of light is really fast. Light will orbit around the Earth 7.5 times per second. And this is just what I'm doing is I'm trying to give you a sense of scale of how big the Milky Way is, and we're going to use the speed of light as that kind of way to interpret that. And so here's another animation made by O'Donoghue, and it shows basically the light travel time between the Earth and the Moon. And again, now the distance between the Earth and the Moon is actually vast. It's really, really big. And so it takes light about 1.25 seconds to go from the Earth to the Moon. So there's a time lag. I mean, there's a measurable time lag between when a signal is sent and when a signal is received on the Moon, right? And so obviously, if you just bounce a signal back and forth, there's a 2-second delay, right? So there's a measurable time delay between our next nearest neighbor, right? And just because the distance is so large. So now, if we look at the distance between the Earth and the Sun, the light travel time is about 8 minutes, a little over 8 minutes, right? And so we're not going to watch this whole video, but you can see, I mean, this is like real time of the 8-minute distance, right? The scale of the sizes of the planets have been inflated, so you can actually see them, but the relative distances are correct, and the speed of light, the relative speed of light is correct as well. So you can see that, I mean, even within our own solar system, the distances are huge, right? So again, Earth to Sun, 8 minutes. So our own galaxy, we estimate that to go from one side to the other, so the diameter of our own galaxy is somewhere between 100,000 to 200,000 light years. It's not well known. I mean, for a long time, people have been saying 100,000 light years, but I read papers somewhat recently where they kind of have an upper estimate of 200,000 light years. So it's, again, the Milky Way is harder to study because we're in it. But yeah, so the Milky Way is huge, and the distances between everything is enormous. So the question is, what is the Milky Way? And this is the question that people have had, since the beginning of time, essentially, right? And so it's just this hazy band in the sky that everybody can see from pretty much every location that's dark. But we give a lot of credit to the ancient Greeks for a lot of modern astronomy, because it's really that culture that really used astronomy in purely kind of a knowledge-based way in trying to understand the universe we live in. Other cultures obviously have used astronomy as well, but it was more for astrology or predictive natures or things like that. But we give a lot of credit to the ancient Greeks. And so the term Milky Way actually comes from the Greek, I'm going to butcher this, sorry, I don't speak Greek, Galaxias Kukulos, which means Milky Wheel or Milky Circle. And so that's where the name of the Milky Way came from. And so the myth is that Hera was sleeping, and the infant Heracles was put upon her to breastfeed, and Hera woke up and pushed him away, and then milk spilled upon the sky, and there you got the Milky Way. And that's the myth as to where the Milky Circle came about in the sky. And then in the ancient Romans, about 1,000 years later, had a similar story for that with Juno and Hercules, which are essentially the same gods. And the story continues on from there. But again, there are different cultures who obviously see the same object but interpret it differently. So I mean, the Armenians, the Cherokee, the Egyptians, everybody. And honestly, my favorite one is the Finno-Ugaric one, is the pathway of the birds. And I just like that because it's a little more scientific in a sense, because they thought that birds actually follow the Milky Way in their migratory patterns from the north to the south. And I think there's some evidence for that for some birds that may actually be true. But I just found that to be a interesting interpretation of nature in their understanding of what the Milky Way actually was. So it wasn't until about 400 BC that really somebody started thinking about what the Milky Way actually was. Like, what is it for real? Is it something of the gods, or is it something a little more tangible? And Democritus hypothesized that what the Milky Way is actually a large number of stars that are so far away that you can't resolve individual stars. That what you're looking at is stars so far away that they just kind of blend together, they smear together, and they just look like a hazy band in the sky. But obviously at that time, there's no way to identify that. There's no way to actually measure that, because like telescopes weren't really used, they weren't invented yet. There's just no way to identify that at that point. This is about 400 BCE. So it wasn't until about 1610 that again, Galileo was the first one to actually point the telescope at the sky and really identify objects, like investigate the heavens, right, with using a telescope. And one of the things he found, and including like sunspots, the phases of Venus, all these other things. One of the things that Galileo saw was that when he pointed just at the sky, there were more stars in his telescope that he could see than he could see with his naked eye. So that led him to believe that looking at the Milky Way and like pointing at the Milky Way, that led him to believe that really the Milky Way is made of unresolved stars, that there are so many stars there that are more that can be seen individually by the human eye. And so it was 2,000 years after Democritus hypothesized this, that it was actually shown to be true. So there's a large gap in time between thinking about something and actually determining it to be correct. So it wasn't until the 1750s that people had good theories, had good hypotheses as to what the Milky Way actually was. And so it was Thomas Wright and Immanuel Kant who basically thought that the Milky Way was essentially just a giant disk of stars. Okay, and so why would they think that? Okay, so this is sorry, it's a low resolution image. I pilfered off the internet. I apologize, but you get the sense of what's going on. And so the reason why we think we live in a disk of stars is because if we lived in a sphere of stars, no matter where you are in the sphere, if you look in every direction, you should see an equal number of stars in every direction you look. So if you imagine you're inside of a basketball, right, and you punch holes in the basketball, everywhere you look, you're going to see the same kind of distribution of holes punched in the basketball, right? But if you're inside of a hockey puck and you punch holes in the hockey puck, if you look along the plane of the hockey puck, you're going to see a lot more holes than you are if you're going to look along, the like top and bottom of the hockey puck if you're inside of it, right? And so a lot of the material is going to be distributed along the plane of the disk as opposed to outside of the plane of the disk. And so when you look at the Milky Way, so let's see if I can get the mouse pointer. So if you look at the Milky Way, this is exactly what we're seeing. So we're seeing all this material along the plane of the disk here and some material outside of the plane of the disk. And if we're located inside of it, this is what we expect to see. Okay, so this is just a computer model of what the Milky Way looks like. And it's really, I mean, obviously this is not a completely accurate representation, obviously, because this is artist's interpretation. But this gives you a sense of what the Milky Way looks like. And you can see, and this will loop through, so I'll show you again. But what you're looking at is a top-down view, and then it's going to an edge-on view. And you can see that the Milky Way is actually a very, very thin object. Okay, there's a bar going through the middle. You can see the bulge in the center of that bar. And then you can see the rest of the disk with the spiral arms. And then you see all that dark material in that same plane as the arms. That dark material is dust and gas within our own Milky Way. And that's blocking out the starlight that's glowing in the arms. And so the Milky Way is actually a very, very thin object. So spiral galaxies, and like the Milky Way, are essentially the ratio of diameter to thickness is about the same as stacking 2 DVDs on top of each other. So the thickness of 2 DVDs is basically the thickness of our galaxy relative to the diameter of those DVDs. So it's a very, very thin object. Okay, so after Wright and Kant, the next kind of step was, okay, if we live in this disk, where are we in this disk? Where are we in the Milky Way? And so William Herschel set about to try to figure that out. And so this was after, we finally kind of determined that we are not in the center of the solar system, right? We are orbiting around the sun. The sun doesn't, like the rest of the solar system, doesn't orbit around us. We're not in a heliocentric universe. Okay, so where are we in the Milky Way? It's likely, since we're not in the center of the solar system, we're not going to be in any special place in the Milky Way either. We're not going to be in the center of the Milky Way. We should be somewhere, right? So he thought, okay, well, what if what I do is just count the numbers of stars in every direction that I can see, and then the direction that has more stars will tell me the direction like toward the center, right? And we should be, if we're closer to the edge, then there'll be less stars in that direction. And so we can kind of determine where we are relative to the center of the Milky Way. Well, so this is his actual count and his distribution for all the stars he could see. And this is where the sun is, so that little asterisk there in the middle. And you can see that it's in the middle, right? So he basically determined that we were in the center of the Milky Way. And what he didn't take into account was dust. So he didn't know that there was dust in the Milky Way that's blocking out starlight behind it, right? So this dust essentially works the same as like, swimming through like a pond with a lot of silt, right? If you're swimming through this pond, you can only see so far through the silt before all of a sudden you just can't see it. You can't see beyond anymore, right? So if you're looking in every direction within this pond, it's going to look like everything is the same distance away from you, right? You're not going to be able to see, very far in any direction. It's all going to be basically everything's going to be the same distance away from you, essentially, unless you look straight up out of the water, then you can see planes and birds flying away, right? But so he didn't know about dust, and that was essentially blocking all the stars beyond a certain distance, which basically put us at the center. But what he did map, so that little sorry, I'm going to use mouse pointer. So this little wedge you see here, this is actually a dust lane within our own galaxy, and these are stars just above and just below that dust lane. So he actually did map out some dust in the Milky Way, he just didn't know what it was at the time. So, okay, so that was what, the late 1700s, about 1800? So 100 years later, there was kind of a breakthrough by Henrietta Leavitt. Okay, so she was essentially a human computer, right? So it's just a person who does computations. And she's basically, I mean, she's an astronomer, right? But I think at that time, women couldn't be astronomers, or they didn't want women to be astronomers. So she helped out an astronomer, but she made an incredible discovery. I mean, one discovery that I'm going to talk about, but there were many, she did a lot of work. She did a lot of great work. But one thing she found was that she found stars that were variable. And these, we call these Cepheid variable stars. And what's special about them is that they pulsate in brightness, okay? And the interesting thing about that is that, so what happens essentially is that they inflate and they get brighter, and then they essentially cool down and collapse and shrink down and get dimmer again. And the period of their pulsation is directly related to how intrinsically bright they are, okay? And that's very important. So just by looking at how fast these stars pulsate, we know how bright they are intrinsically. So what that means is, so this is the relationship. This is the period luminosity relationship that she came up with. So essentially, I'm going to use a mouse pointer, sorry. So essentially, if the stars pulsate relatively slowly, then they are very, very bright intrinsically. Or if they pulsate very, very quickly, relatively quickly, then they are dimmer. Okay, and so there's a nice relationship between the pulsation rate and the intrinsic brightness. Okay, so what makes these important is that these work as standard candles. So now we know how intrinsically bright these stars are. So now we can put them at different distances away, and we know how bright they're supposed to be, and now we can measure how bright they look, and that will actually tell us the distance away that these stars are. Okay, so just like taking a bunch of candles you buy at the store, right, that they're all the same, and you put one on your table and you put one in your backyard, right? Intrinsically, both of those candles have the same brightness, but if you move one further away, it's going to look much dimmer, right? And so by knowing how much dimmer, you can actually calculate how far away that candle is from you. And so you can do that with these stars. So the nice thing about that is that you just have to look for these pulsating stars, measure how bright they appear to you, and you can figure out how far away they are from you. So Harlow Shapley took that idea and looked for Cepheid variables in various objects. He looked for Cepheid variables in globular clusters. So these clusters of stars that are found both in the plane of the Milky Way and outside the plane of the Milky Way. Okay, so, and by looking at, so he assumed that these globular clusters are basically evenly distributed throughout the Milky Way, like around the galaxy. And so the center of the distributions should be at the center of the Milky Way. So all he had to do was find these Cepheid variables, measure the distances to these clusters, and then just basically trace to the center, then basically line them all up, and you can trace to the center of the Milky Way and find out where the center of the Milky Way is. Okay, so he did that. And what he saw, so we'll look at the central plot here. So all these little pink dots are these globular clusters, and he measured the distances to these, and they're all kind of centered around this yellow dot right here. And this is where we are right here, and this is the sun. So I forgot what the first date was. Was it 1600s, 1700s or so, where we first figured out that we thought we were at the center of the Milky Way. So it wasn't until 200 years later that we now we're able to definitively determine that we are not at the center of the Milky Way anymore. We are kind of off to the edge. We're about halfway between the center and the edge. So we're about 8 kiloparsecs away from the center of the galaxy. So things are happening a little more quickly here. I mean, still centuries, but breakthroughs are being made more quickly than in the very beginning. Okay, so so now what we do is we kind of break down. You know, we're now able to kind of using modern technology, modern telescopes and things like that, and we're able to understand, you know, distributions of stars and their metallicities and their, you know, what they're made out of and things like that. We now can break the Milky Way down into different components. And so we have the bulge of the Milky Way, where we have much older stars. We have the thin disk, where we have young stars and gas, where new stars are being formed. We have the thick disk around that. And we also have the halo, which is basically surrounding the entire disk of the galaxy. And this is where we find globular clusters, some of the oldest stars, and in the halo as well is where we tend to have a lot, the dark matter basically tends to reside. Most of it is out in the halo part of the galaxy. Okay, so all right, so now we know we live in a disk of stars. We know we don't live in the center of that disk. How do we know that the Milky Way isn't just a smooth disk of material? How do we know that it actually has spiral arms? Well, we do that by looking at the distribution of gas throughout the Milky Way. Okay, so so this plot is actually, this is a lot more complicated than it needs to be. Really, all you need to look at is the rightmost plot, the middle plot there. So basically, if there was an even distribution of gas throughout the disk, so basically if there were no spiral arms, if you measure basically the velocity of gas rotating around the center, orbiting around the center of the galaxy, you would just have a smooth distribution from where we are out to, like, as far as you can see, right? You would just see a smooth velocity curve of just gas clouds all the way out. Okay, that is not what we see. We see that gas is actually concentrated in regions and rarefied between those regions, and that's what the central plot is. So you can see these peaks right here, A, B, and C, in the central plot. This is where gas is actually concentrated, and we're missing gas between those peaks. So that leads us to believe that there are actually regions of gas and regions where there isn't gas. So that leads us to believe that there are actually spiral arms in the galaxy. So much like spiral arms we see in other galaxies, we think that exists in our own galaxy. Okay, and so this is a sketch of what we think our own galaxy looks like, all the spiral arms in our own galaxy that we can identify. And you can see, so we are here. So this little yellow dot right here, this is where we are. Here's the galactic center, here's the bar. And then these are all the different arms that we can see, and the gas clouds kind of associated with those. And you can see that there aren't, in some regions, there aren't full arms. There are like these spurs, right? So there is, so we think that we actually live on this spur right here that isn't a fully developed arm that kind of goes all the way back down to the center. And so these dashed lines are where we can't see the spiral arms anymore. There's just so much material that we just can't identify it anymore. So that's just kind of an approximated map now, because we don't think arms just stop. We think they're, you know, everything should be symmetric essentially in our own galaxy. So we can't see beyond the center of our own galaxy either. So there's a shadow. And so we think, you know, we can see this part of this arm here, we can see this arm over here, but we think that it's probably connected right here. We don't think that there's some kind of weird discontinuity, obviously. So we make some assumptions as well. But this is what we think our own galaxy, this is like our own roadmap to this galaxy. Okay, so here's a little better artist interpretation of that. And so you can see here's the Orion spur where we are. So the sun is now here at the bottom. So the interesting thing here, so I didn't really talk about the bars yet. Let me talk about that, because this is one of the things I'm really interested in. So the bars in spiral galaxies are actually really interesting objects, in my opinion. They're linear structures of stars without a lot of dust and gas in them. And what they are, they're basically rotating kind of linear structures of stars that create like gravitational torques within the galaxy. So it basically redistributes material throughout the galaxy, gas clouds and things like that. And so when we look at galaxies within the universe, about 2/3 of spiral galaxies are barred galaxies. Normally, when you think of a spiral galaxy, you kind of think of like a pinwheel with like a ball in the center and arms just kind of coming out of that ball. That's only about 1/3 of spiral galaxies. Barred spirals make up most of the spiral galaxies we see. And so we think our own Milky Way is a barred spiral galaxy. The weird thing is that there's data to suggest that there are actually two bars within our own galaxy, kind of overlapping each other. And so that's what you're seeing here in this mock-up. You can see this this wider, fatter bar right here, and you can see this longer, thinner bar right here. And so you can see that they're kind of offset from each other, but they're basically centered on the center of the galaxy. And that is weird because I study barred spiral galaxies and I've never seen that. That has not existed. That does not, as far as I know, that doesn't exist in any external galaxy other than our own. So my feeling with this is that at some point somebody's going to find some data to say, okay, well, the long bar probably isn't correct, or that short bar is probably not correct, and it's going to fall. It's going to collapse down to a single bar. I don't think that there truly is two bars. I don't think there truly is two bars within our own galaxy. So these are real galaxies that are probably very similar to our own. And so you can see here the image on the left here. This is a spiral galaxy. Obviously, it has spiral arms. You can see the bar. And if you look around the outside of the bar, you can see that there's what looks to be like a circular feature, right? A circular ring around it. This is actually when I talked about the redistribution of material by the bar rotating. These bars actually create these rings surrounding them. And so we think our own Milky Way actually has one of these rings as well, one of these what we call resonance rings. And you can see the galaxy on the right is similar to that as well. And this galaxy actually has a pair of bars. So it has this main bar right here with the arms coming off of it. But if you look in the center here, there's actually also a nuclear bar right here. And there's some evidence that suggests that we may have a nuclear bar in our own galaxy as well. But again, also a resonance ring. Okay, so how are these spiral arms actually generated in spiral galaxies? Because when we look at spiral galaxies, I mean, they form relatively quickly, and then their spiral structure is maintained over a long period of time. So how is that actually maintained? Okay, so these are really the three hypotheses here of how spiral arms can form and potentially be maintained. Okay, so the animation here on the left is essentially a rigidly rotating disk. Okay, and what you're seeing, it's basically like a record, right? If you draw spirals on a record and you just have the record rotating, this is what you're seeing on the left animation. And we know that's not correct because we can actually measure the velocities of gas and stars in the spiral arms. We know that it's not doing that. It's not rotating as a rigid object. The arms actually rotate differentially. So basically the material near the center is orbiting faster around the center than the material on the outside. It's not rotating as a solid object. So that's not correct. The middle animation basically says, okay, well, if you have, if you have differential rotation where the things on the inside track are moving faster than the stuff on the outside track, you can naturally create spiral structure. But the problem is, over a long period of time, that spiral structure winds up until it gets tighter and tighter and tighter, until you can't identify spiral structure anymore. And that's what you're seeing in the central animation here. And so eventually, toward the end of that animation, it just looks like a mess. It just looks like a ball at that point, with very, very fine arms, very closely gapped. As the gaps are very small. And so that's not what we're seeing either in spiral galaxies, in our own or others. So the best hypothesis that we have is something called, oh man, I lost the word, density wave theory. So the idea is essentially that stars and gas and dust are actually orbiting into and out of regions of high density. So when these gas clouds enter these regions of high density, they collide with each other, form new stars, ignite, light up, and show you where those high density regions are by basically lighting up those arms. Okay, so let me show you a little better animation of what that looks like. But you can see that the animation on the right, that density wave theory, it maintains those spiral arms, right? You don't have the winding problem. Nothing's rotating as a rigid object. You have differential rotation. All of that happens. Everything that we observe happens, and you can keep the spiral structure for a long period of time. Okay, so this is a really cool animation that I found by this YouTube user, Kev Pluck. basically what you're looking at is just, these are all supposed to be gas clouds orbiting around the center of orbiting around the center. They're orbiting differentially. And what we do is we just elongate the orbits from circular, and then we rotate the orbits. And when you do that, all of a sudden now you create spiral structure immediately, right? And so what's happening is, so nothing is really changing. The orbital velocities and everything are the same as they initially were. It's just now the orbits are just offset from each other. And by doing that, you end up with regions of higher density, where the gas clouds move into and out of those regions of higher density, right? And so if those gas clouds are very large, they'll collide with each other, form new stars, which will light up and then show you where those regions are. And this is how you can create these, grand design spirals that have like two really massive arms. Okay, so that's essentially the disk of our galaxy. So now if we move out to the outer halo of our own galaxy, so what's going on out there? So it was in the 1970s when Vera Rubin started measuring the outer regions of galaxies. So what she did was she measured the velocity of stars, near the center, and then she measured the velocities of gas further away from the center, as far out as she could measure. So basically where there was almost no more starlight at all. And so what she expected was that like all the mass should be where all the light is, right? Where all the stars are, where everything is glowing, that's where all the mass should be. So what should happen is, as you move further away from that mass, the velocities of the objects that you're tracing, that you're following, right? The orbital velocity should go down, right? Because you're enclosing the same amount of mass, you're just getting further and further away from it, right? And so that's what she expected. But what she measured was actually this top graph right here. So she measured the starlight, and then she measured the gas. And what she saw was that the velocities, as you got further away from the center, didn't go down, they actually went up, or they stayed flat. And what that means is that as each one of these data points here at a different radius, for each radius getting further away from the center, you're enclosing more and more mass as you get further and further away from the center, right? And it's this mass that's not glowing that you're enclosing. Okay, so as you get further out from the center, you're enclosing more and more mass within this galaxy. And all this mass is not glowing, which means it must be some kind of dark matter, right? And so when we look at every single galaxy we look at, including our own, they all behave this way. The gas clouds and stars and everything in the outer edges of galaxies are orbiting around not only the mass in the center, but also all this dark matter that is within that orbital radius as well. And so if we look at, again, the density wave theory here, and again, I apologize for the stuttery animation, but if we don't have dark matter, you have this animation here on the left with density wave theory, and you can see the rotation, the movement of the gas and stars in the outer arms there. Everything is moving very, very slowly on the outer edges. But when you include dark matter, when you have that flat rotation curve on the outer edges, you can see that everything is moving much faster. The orbits are much faster. And that is actually what we're seeing in our own galaxy and other galaxies. And so this is just a schematic of what our own rotation, the rotation curve of our own galaxy. And you can see where we are and what we expect. So this dash curve here is what we would expect the rotation curve to do, and the red line is what it actually does. And so from this, what we know is that the total mass of our own galaxy, only 10% of it comes from visible matter. 90% of the mass of our own galaxy is dark matter, is matter that we don't know what it is. It has gravity, and that's all we know. We don't know anything else about it. But obviously people are working on that, but right now there's no definitive answer as to what dark matter really is. Okay, so even though now we're looking at like an all sky view in a different wavelength of our own galaxy, this is actually telling us something about the nucleus of our own galaxy. Okay, so we talked about the outer halo, so now we're going to zoom down into the nucleus of our own galaxy. Okay, so looking at this, again, you can see the disk of our own galaxy, right? It looks really bright along the plane, and you can actually see the disk there. And so what this is actually a view in the, this is what Fermi, so this is in the gamma ray, so this is high energy material. So what you're looking at is like neutron stars, supernovas, things like that. But what you can see, if you look in this image, so you can see, oops, so you can see the plane, I gave it away. You can see the plane of the galaxy, but you can also see these faint little blobs up here and down here. Okay, and this gave us the first indication that something different is happening. And so what we know now is that there are actually remnants of these giant lobes that are perpendicular to the disk of our own galaxy. So we call these the Fermi lobes. And what it is, it's remnants, it's gamma ray emission from remnants of these giant lobes that used to be glowing both above and below our own galaxy. So where do these lobes come from? What does that actually tell us about the nucleus? So when we look at other galaxies, some galaxies have these jets that kind of squirt from the poles of the galaxy, right? So in this case, this is a Centaurus A galaxy, and you can see kind of here's you can see the disk right here. You can see these jets right here, and then you can see these kind of bubbles, these little jellyfish-looking things right here, right? So these jets are actually streaming out particles at incredibly high velocities, and these particles are slamming into what's known as the intergalactic medium. And it's basically because they're at such high velocity, when they hit those, they create these shock waves that then glow in the gamma rays. And so, so if we zoom in, if we go into the nucleus, if we get closer to the nucleus, what we're going to see then, like for instance, in like Centaurus A, you're going to see a disky torus near the very center of the galaxy, and the jets are going to come out of this disky torus. Okay, so what's in this disky torus? Well, if we zoom into that, there should be a supermassive black hole in the center of this torus. And what's happening is, so in this image here, you're looking, so a torus, for those that don't know, a torus is essentially a donut, right? And so what you're looking at is these right here, this is the walls of the donut, and you're inside the donut here, and then you have this thin disk of material right here, and all this material is spiraling onto this black hole, okay? And so this black hole is incredibly massive, and this material is spiraling into it, and as it does that, it's spiraling faster and faster, and the material on the inside track is moving faster than the material on the outside track. And from that, you get viscosity, which gives you heat, which turns the gas into a plasma, which is charged particles. And when you have charged particles moving, you create a magnetic field. And by doing that, some of those particles get caught in the magnetic field, which is perpendicular to the plane of the disk. And then they get shot at very high velocities, both above and below the disk of material. And these get shot from this tiny little guy in the center of the galaxy all the way out past the plane of the disk, out into the intergalactic medium, shocking the intergalactic medium with such energy that it creates gamma rays that we can see. Okay, so that's fantastic. So what we think is that at one point, the Milky Way actually had an active black hole, in that it has a black hole in the center, and it used to have a disk of material where stuff was falling into it, creating these jets that then interacted with the intergalactic medium. But what has since happened, since we just don't see the jets anymore, is basically shut down, and now the glow is starting to fade away. So just like when you turn off the heating element on your electric stove, right, you're left with the kind of glow and the heat, and eventually it's just going to go away, right? And so that's what's probably going to happen with the Milky Way. So this is good. So that was good evidence for a black hole existing in our own galaxy, right? So what has happened more recently was that a group at UCLA, they managed to get a lot of telescope time, and they observed stars near the very center of the galaxy. And what they did was, over a period of years, they just tracked the orbits of these stars around an unseen object. Okay, so all these stars were orbiting around something that wasn't visible. And so that white star that you see in the center, that's actually the invisible object. And the colored blobs, those are all the actual stars. And so by tracking these orbits, we can basically use Kepler's law for each one of these stars to determine the mass of the object that each star is orbiting around. So let's say there are, I don't know, 10 stars here, right? So we get 10 independent measurements of the mass of the object that each star is orbiting around. And what we've determined is that the mass is 4 million times the mass of the sun, but in a space that's only 17 times the diameter of the sun. And what that means, the only thing that could have that much mass and that small of a volume is a black hole. And this is what's known as a supermassive black hole. So any black hole that's basically 1 million to 1 billion times the mass of the sun is known as a supermassive black hole. And so the video that you're seeing here, this little GIF that you're seeing here, is the actual data over those period of years of these stars orbiting around the unseen object. And you can see as time goes on, the resolution gets bigger. It's because they upgraded the instrument in the meantime. So you can actually see that in the time lapse. So the Milky Way has a supermassive black hole that's 4 million times the mass of the sun. And when we look at the other galaxies, essentially every galaxy we look at also has a supermassive black hole in the center. And it's unknown why or how that can happen. And that's a topic of active research, and that's something that I work on as well. Okay, and honestly, the best evidence for the supermassive black hole now is from the Event Horizon Telescope. And the image on the right is one that was released, I think it was within the last year, of the actual disk surrounding the supermassive black hole at the center of our own galaxy. And so you can see the glow here of the disk, and this shadow right here. This is where the supermassive black hole is. And so the interesting thing is, so this was done previously. This was done with an elliptical galaxy called M87. And you can see the disk here on the left. This is the one from M87. This M87 image was likely easier to obtain than the one for our own galaxy. And the reason is because M87 has jets. And because it has jets, we know the orientation of the torus. And we know that it's active. So we know it should have a disk. So imaging it, and also elliptical galaxies don't have a lot of dust and gas to look through. So it's kind of an easier target than it is our own galaxy. For our own galaxy, we don't really know the orientation of the disk because there's no jet anymore. And you also have to look through a bunch of dust and gas. And it's not 100% certain that there would be any kind of disk that would glow, just because we don't really have a strong jet anymore. And so this disk, even though they look to be about the same size, I think the disk on the right for our own galaxy is actually much smaller than the one on the left. Okay, so we're getting to the end. So basically, how did the Milky Way come about? And that's basically the origin of every galaxy. Like how do galaxies actually form? So when we look at the timeline of the entire universe, the universe has been around for about 13.5 billion years. And we can see back to about 300 to 400,000 years after the Big Bang, but we can't see before that. Okay, but what we can see is that what we do know is that the first stars seem to have formed about 400 million years after the Big Bang, but the first galaxies also seem to form about the same time. Basically, you get the first stars and the first galaxies like rapidly after the first stars, and so that's unusual. So how do we grow galaxies so fast, and how can we end up with these giant spiral galaxies like the Milky Way? And how can they last for so long? So the current hypothesis is that there's something called hierarchical evolution or hierarchical merging, which is basically you start out with like small little globs of stars or in gas that then kind of merge together to form a larger glob, and then a smaller glob merges with that and makes a larger glob, and so on and so on. So you end up with like smaller objects merging together to form larger objects. So you're starting out with like a very large base, and then you're basically working your way up into a pyramid of one large object. So this simulation kind of shows you hierarchical merging in a small volume of space. And again, I apologize that that's so jumpy on the screen. But you can see the bright objects are these small, tiny proto-galaxies. And you can see that all this gas is starting to condense, form these streams, and these galaxies are kind of forming from these condensed regions, and they're all being attracted by gravity to each other, and they're all going to combine and coalesce into a larger object. And I do want to let this run for a little bit because right now it doesn't look so impressive. It still looks really tiny, but eventually we're going to end up with a very large spiral galaxy in this simulation. So I'm going to let this play just for a minute. And you can see all these tiny little satellite objects kind of whizzing by or being absorbed into the larger galaxy. And here you have a major merger of two galaxies. Okay, so now here's where the fun stuff happens. So now everything is really starting to coalesce and form a large spiral galaxy. And actually, the nice thing about the kind of stuttery animation is that you can kind of see the bar forming in the center as well. Because on my computer, it's moving so fast you can just see a spinning linear object, but here you can getting more of a strobing effect. But yeah, so now you can see all these little clumps kind of forming together. And so an active area of research now is looking for ultra faint dwarf galaxies around existing larger spiral galaxies as well, to kind of show evidence for this hierarchical merging in the local universe. So I actually have a colleague who's working on that as well. And she's just taking really long exposure images of ultra faint galaxies using large telescopes. But the James Webb is actually going to shed a lot of light on this. I guess pun intended on that. So obviously this is the James Webb before it was launched, and all the people working on it. And this GIF kind of shows you the capability of the James Webb. So I hesitate to say the worst image, but the lower resolution, not so deep image is actually Hubble, and the quote unquote better image is the James Webb. And you can see the James Webb again. So the James Webb has higher resolution, but it's also looking in a different wavelength range than the Hubble as well. So it's looking more into the infrared, which allows you to look at things further away. And so what we're doing is with the James Webb, we're actually looking further back in time as well. And so you could see, And so what you can see is all these faint red objects in the background are actually being brought out into the foreground. You can actually see these faint objects. So so now with the James Webb, we're gonna be able to start to see some of these very faint proto-galaxies. We're gonna see some of these first galaxies forming from the hierarchical merging. We should be able to see that. And that should actually put the nail in the coffin as to how galaxies actually form. That a hierarchical merging is no longer just, the prevailing hypothesis, that it is a leading theory as to how galaxies form. Okay, so what is the ultimate fate of the Milky Way? So we have the Milky Way now. It's this kind of stable, large, very massive spiral galaxy. But as I mentioned, we're also near, the Andromeda Galaxy is also a galaxy that's relatively nearby, because you can see it with your naked eye as well. And what we've determined, what scientists have determined somewhat recently, is that the Andromeda and the Milky Way are actually on a collision course. So in the future, those two galaxies will actually collide and merge. And when that happens, things are going to get scattered. Things are going to get messy. And eventually what will happen is the gravitational attraction of both of those galaxies and the scattering of the stars, dust and gas and everything, neither galaxy will actually survive that. They will both merge into one final form, which will then be an elliptical galaxy, which no longer has dust and gas. It will just have old stars. And then those old stars will just kind of burn out and fade away, and then that'll be it. So no more new stars will be formed, and we'll just be left with kind of a ball with no real structure to it anymore. And then those stars will just kind of fade away, and that'll be the end of it. But to give you an idea of what it'll look like from Earth, NASA made a really cool set of images. So again, so the solar system is 4.5 billion years old. We're about halfway through the life cycle of the sun. So we have about 4.5 billion years to go. So if you're around during that time, the sky is going to look really different. So in the present, so in these images, the top left image shows you kind of the sky now. You can see the Andromeda Galaxy in the upper left quadrant there, that little linear thing near the Milky Way. In 2 billion years, the Andromeda is going to look a lot bigger and a lot brighter because it's heading right at us. 3.75 billion years, that's when stuff's going to start to happen. And then things are going to happen very quickly. So 3.85 billion years, things are going to get scattered. You're going to have gas clouds colliding. You're going to have new stars forming. It's going to look fantastic. 3.9 billion years, again, very short time period. Again, things are going to be changing rapidly. The sky is going to be probably pretty bright. But then after just about the time the sun is going to burn out, things are going to get less interesting. You're gonna like things are gonna kind of settle down. The merger is gonna kind of approach its completion, and then at 7 billion years, we're just gonna be living in that elliptical galaxy now. So now, if you know, in whatever future we live in, if things backtrack right, and somebody again is thinking about like, oh, what is the shape of the galaxy we live in? It's no longer going to be a disk, right? We're going to be living inside the basketball. So now the distribution of stars is going to be essentially even everywhere, right? It's no longer going to be concentrated in a band in the sky, and that's no longer what they're going to be able to see. And so ultimately, we now live in a spiral galaxy, but we're here in the future, we're going to be living in an elliptical one. And that's it. All right, thanks. And if you guys have questions, online as well.
Thank you very much.
Yeah,
fantastic. I don't see any questions in the chat, so I guess we'll ask first here in the room. Any questions? Please raise your hand, and I'll pass the microphone around. And if not, I've got several myself. So, Patrick, what is the approximate rotation rate of our sun around? How often do we make an orbit of the supermassive black hole?
Yeah, I think at our radius, I think it's 200 million years for one orbit. Don't quote me on that, but I know it's hundreds of millions of years. Okay. Yeah. Is it 230? All right, close.
Yep. We did get a question here from Robert. Any suggestions for a Milky Way motion simulator for a Windows PC that includes our solar system?
Oh man. Man, I don't know of one. I do remember seeing an animation that somebody made. Mm-hmm. It was more artistic than realistic, but if you do make a simulation like that, I mean, not only does the sun orbit around, it's not essentially not in a perfectly circular orbit. Obviously, it's an elliptical orbit around the center, but it's also not entirely in the plane of the Milky Way either. It actually orbits in the Z direction as well, so it kind of bobs up and down a little bit. So I know that data is available. So if you wanted to make one, you could totally do that and simulate the sun orbiting around the Milky Way.
Budding programmers.
Yeah.
No. Frank.
Now he was talking about that great merger.
Mm-hmm.
If any of us or any human race would still be existing at that time, would that merger be dangerous for us?
Yeah. So no, I don't think so, because the thing is with galaxy mergers, when galaxies merge, galaxies are essentially all empty space. There's really nothing in them, right? All the mass. Multiple things. Okay, so stars themselves will not collide. The stars themselves within galaxies, when they merge, they actually just get scattered. The chances of any two stars actually colliding with each other is very, very small, just because the relative mass to diameter of stars and the relative distance between them, the distances are so large that the cross-sectional area of a merger is so tiny that that'll essentially never happen. But because they're so gravitationally dense, they can get scattered. So you get stars flung out all over the place. The gas clouds, though, the cross-sectional area of gas clouds relative to the separations, the cross-sectional areas are very, very large. So the gas clouds will interact, they will collide. And so when you get that, then you get new stars forming. So if you happen to be near a gas, so if the sun gets scattered out and it happens to be near two gas clouds that are colliding and new stars are forming, you're going to get a lot of high mass stars forming that are going to create a lot of high energy photons. So a lot of ultraviolet, things like that. And these really high mass stars that form, they're going to burn out very, very quickly, and they're going to explode as supernovas. So if our sun happens to be near one of these clusters of stars that happen to have a lot of high mass stars in them, and then they all go supernova, in a short amount of time, and we happen to be near that, that could be detrimental to life on Earth. But like, for instance, our own solar system, I think the thing we have to be most worried about is just the sun turning into a red giant. I mean, even if the sun got scattered, all the planets are so bound to the sun, like it's not going to all of a sudden be jerked away. Everything is just kind of going to start drifting in a different direction in the galaxy. It's not going to, all of a sudden be jerked away and the planets are just going to be left hanging there. Everything's just going to move as one object.
It's possible that NASA could build a telescope that would see all the way back to the Big Bang, and what would be there before the Big Bang?
Well, so I think the potential for a telescope, so optical, anything that uses electromagnetic radiation can only see to 300,000 years after the Big Bang. We can only see to the cosmic microwave background. That is it for electromagnetic radiation. We can't see beyond that. But the gravitational wave telescopes that are being built, the gravitational wave detectors, if we create many, many more of those with ultra high resolution, eventually, because those do not use electromagnetic radiation, those are actually looking at ripples in space. They're looking at space itself. And so potentially, again, this is more science fiction than science fact, but potentially we could break through that cosmic microwave background boundary and look all the way potentially to the Big Bang. Again, it's going to be a feat of technology to do that because the signal is going to be so weak, but potentially you could do that.
And of course, I guess you could say before the Big Bang, you would have to read Genesis chapter 1, verse 1.
Okay.
All right, we got a question in the back here.
Yeah, thanks. Recently there have been some press reports that James Webb is seeing galaxies that are bigger than they expected them to be. And some of those press reports are a little, I mean, they're tied up with some weird theories, but
Yeah.
do you have any info about that?
No, I think I saw a headline about that. Yeah, I mean, I can only speculate. So if that's true, if they are seeing galaxies larger at that period of time than they expect, that's going to make things difficult. Because that means the merging process is happening very, very quickly. Again, I don't know what that means. Again, and it could be wrong. It could be like a spurious result. Is that true for everywhere? I don't know. Yeah, I think again, like everything, we need more data.
When we observe the Milky Way in the sky, is part of what we're observing the center?
When you mean like when you look at it with your own telescope and stuff?
Or,
Yeah.
with naked eye.
Yeah. So you can. Well, you're not seeing the nucleus, but you can see the bulge. So let me go back. Sorry, let me do this. Let me go back to a schematic. You can see the core of our own galaxy. So let me use this as an example. So these are real galaxies. So what you can, again, let me use the mouse so people online can see. So you can see this portion right here. So this bulge region right here. And so the nucleus is within that bulge. I mean, it's at the very center and it's so tiny. I mean, it's almost insignificant in this image. It's insignificant in this image. But you can see this. And so that yellow, when you look out, when I showed you those images of the Milky Way in the sky, the yellowish portion that you see, that's the bulge of our own galaxy. That's the center of our own galaxy. And I guess I didn't point it out well enough, but when I showed you kind of the diagram of the different components of the galaxy, you had the bulge, the outer halo, the thin and thick disk. The bulge is all these older stars. And the older stars are not going to be blue. The young stars are going to be blue. And so that's why the bulge actually looks kind of yellowish orange. It's because it's composed of mostly older stars. And so if you go into a really dark area, so the only time I've ever seen it was in Hawaii, in the middle of nowhere. I mean, like in the middle of pitch black darkness. But you can actually see all of that color, and it's amazing. Like the first time, I mean, I work with galaxies. I know, the coloration of them, but I've never seen that with my own eyes, and that was fantastic to actually see the yellowish orange of the bulge, and then the band outside of that, which is actually the disk where all the young stars are. To see the blueness of that and see the color difference is fantastic. But yeah, you can see the bulge, you can see the center in that sense. Yes. Yeah. So yeah, let me show you that. Yeah. So that's those not the very first picture, but the like this set here, this is actually a little more realistic as to almost what I saw in Hawaii. I mean, this is, I'd say the one on the left is a little more closer to what I've seen in Hawaii. And so this is looks kind of yellowish here. And then if you could see the edge, like this is a little further away from the center, and this actually looks a little more blue. I'd say this is the closest to what I've seen in reality, is this left image. Yeah.
Time to book a flight to the Big Island.
Yeah. Right.
And I'm assuming that's also very high up. You're probably 10,000 feet.
No, I was I stayed at an Airbnb near the volcano.
Oh, wow. Okay.
Yeah, I mean, but it was like, I mean, I think it was like new land that was from the volcano or something like that. I mean, it was really dark out there. It was cool. I've never been in a place like that.
Awesome. You also mentioned velocities, and again, just coming from a complete amateur's point of view, because we can't see motion in at least what we see in our telescopes.
Right.
How are you able to calculate the velocity of things? And
Right.
again, not looking for
Right. Yeah.
the lecture, but
No.
it's always just been a surprising. I understand it can be done. It's just
Right. Yeah.
obviously
So
why.
yeah. So I mean, the two main things that so one of the key tools that astronomers use is spectroscopy, right? So that's basically you take the light that's given to you by whatever object, and you send it through a prism and you break it up into its component colors, right? And when you do that, if it's composed, so let's say you're looking at hydrogen gas, right? The hydrogen gas, that light is not all white light. It's not like light coming from a light bulb. It's wavelengths of light that are being emitted by the gas. And so when you break that up into its component colors, you're going to end up with individual lines of light, of color, essentially. And what you do is, in a laboratory here on Earth, you look at those spectral lines, you identify their spacing, and you identify what wavelength they are. And what happens is when that gas is moving away from you, those lines get shifted to longer wavelengths. And when it's moving towards you, those lines get shifted to shorter wavelengths. So it's a Doppler effect. Just like an ambulance coming towards you, the sound gets higher pitched. When it goes away from you, it gets lower pitched, right? The wavelength gets stretched out. So it's the same thing with light. And so what we do is we look at gas clouds or stars that have these lines of light, and we look at how much they've been shifted. And the amount of shift tells you the velocity. So if it's only shifted a little bit away, then it's only moving slowly away from you. Or if it's shifted a lot to shorter, it means it's moving very quickly towards you. And so you can determine the velocity that way. And so that's a very important tool in astronomy, is doing spectroscopy of objects. So that way you can get the velocities. Yeah.
And then so you've got to, I assume, then measure different parts of the same galaxy to I guess, eliminate the actual motion of the galaxy to you versus how the arms are rotating. Okay.
Right. Yeah. So when we measure the rotation velocity of a galaxy, really what we do is we take a slit and we run it through the center of the galaxy, like from the edges through the center. And so what happens is, if obviously if the galaxy is face on, you're not going to get any velocity. You're just going to get the whole velocity of the galaxy, right? But if it's tilted in some fashion, and you could do the math for that, but essentially if it's tilted in some fashion, some of it's going to be moving towards you and some of it's going to be moving away from you. And the center isn't moving away or towards you. So you get the velocity of the galaxy itself, and then you get the velocity of the arms relative to the center. And so it's a very useful tool.
Fantastic. Fantastic. Any other questions here in the room? All right.
You were to point the Webb telescope somewhere.
Yeah.
To learn more about this topic, where would you point it?
Oh, man.
Find out.
Learn about this topic, about the Milky Way. Oh man. Well, that's a good question.
Cygnus.
Yeah. I mean, yeah. Well, I think what you want to do, well, I don't know. I mean, I think you kind of want to point it at the center of the galaxy though, too, because the nice thing about the infrared, if you're at the right wavelength of infrared, you can penetrate all that dust and stuff too. So yeah, I don't know. I mean, and also the bar of the galaxy as well is composed of old stars. And again, that's in the plane of the disk. And so you're going to get a lot of dust obscuration as well. So potentially using the James Webb to kind of map out the stellar structure of the bar as well might be useful. And maybe that could eliminate the 2-bar problem. But yeah, I don't know.
Time to call,
Plant in binoculars.
Yeah,
I think time to call Hopkins. We'll see what we can do.
Yeah.
Get you some time on James Webb.
Speaking of the James Webb, I was going to ask, are you using the data from that? And do you have any proposals in for it to be pointed at something?
yeah. No, I don't actually. So the James Webb. Yeah, so right now, I think what the James Webb is mostly doing is doing like its main targeting, right? And so I think this is, well, I can't say this definitively, but I think the program itself has identified targets that it's trying to do immediately, like basically the high benefit, like kind of low cost targets, right? But people are proposing for it to do their own individual observations and stuff, and I'm sure that's getting done in between. But I think a lot of like all the data that's coming out, I think it's all just the general, like, this is going to be fantastic. We need to do this first. But yeah, but like in the future, because it has a certain like lifespan, right? Where it's like the mission is done here, and now we're just going to see how long we can keep on doing it. Like it has a main mission. Beyond that, that's when you're going to start to get a lot of astronomer proposals being done on the James Webb as well. But me personally, I mean, I work in the local universe, so I work with local galaxies because I try to understand like kind of the end products of galaxy evolution and the structure and stuff. So I don't know. I mean, I do a lot of. I mean, now what I'm doing is a lot of like kind of large scale kind of statistical stuff. So I don't know. I'm waiting. I'll wait for somebody to do like a survey, a galaxy survey, and then I will use their data.
Okay, last question.
How come our telescopes can't see past the 400,000 years?
Oh, right. Yeah. So basically because there was no light before that. So it's essentially that's the first light that was being emitted by the hot universe at that point. So what was happening before then, the galaxy was so hot that it wasn't transparent at that point. And then essentially it rapidly expanded, and the volume got so big that that stuff could start kind of cooling, and that light could now escape out into the rest of the universe. Before it was kind of trapped in there and just kind of swirling about, I guess, in a sense. But yeah, so the issue is like there's no, I mean, that's really the limit of what we can see, because that is like the background radiation of the universe. It's basically the background heat of the universe. So everywhere you look, the radiation is everywhere. And so the only way to look earlier than that is to not look using, electromagnetic radiation, not using light. You have to think of something else. And I think gravitational waves is probably the way to do it. So yeah.
One more question.
Yeah, so you're talking about the cosmic background radiation. So something I've always wondered, or I've asked lots of people who are have a degree in astronomy. So I'm going to put you on the spot and see what your take is on it. So you have the cosmic background radiation. Now, I mean, you see that like famous map that almost looks like a map of the world. It's just like this big globe and whatever.
Yeah.
Is there a way that you can look at that map and say that, okay, well, it extends over here, it's then over here, and get an idea exactly the point where the Big Bang originated? Because we talk about, we're the center of the solar system, we're center of the galaxy, we're the center of the universe. What about the center of the Big Bang? Can you figure that out?
Well, no, because the issue there is the Big Bang happened everywhere, right? I mean, the problem, all of space came from the Big Bang, right? So any point in space was at the Big Bang. So there is no central point to that because basically all of space is from that, right? So
that's almost like you're saying there's some credence to that steady state theory a little bit.
The steady state.
Trace it back where the center of the universe is.
Well,
that's where the Big Bang originated. Even though we were all there,
right?
We've expanded away from that center. Why can't you find that center?
Well, because Well, the thing is because so when you map out everything that's happening now, right? Everything is moving away from everything else, right? So no matter where you are, no matter where you stand in the universe, you're moving away from everything else, right? So if you backtrack that, everything was closer at a certain point, and everything was closer at a certain point, right? So where's the center of that? If you stand here, everything is moving towards you. If you backtrack it, right? If you stand there, everything's moving towards you. There is no center, right? Everything is just getting closer and closer together. So
things that are moving, like if you're in a sphere,
yeah,
things that are beside you are moving away and out at the same time.
Yeah.
People, something directly opposite the sphere
Mhm.
is moving exactly away from you.
Yeah.
So why? I guess.
I mean,
the problem system, we can't see far.
well, but we interpret.
Can't see the other side.
Right, but we assume that everything. Oh yeah, sorry, you didn't have the microphone. Yeah, sorry about that.
Yep.
Sorry, Zoom people. Yeah, but I mean, the thing with that is, but we interpret that as, right. I mean, we're not in a special place in the universe, right? So even if we can't see the other side of the universe or whatever, right? We assume that everything is the same over there, right? So the thing is, like, if I stand here and everything is moving away from me, if I stand here, everything is moving away from me. The same thing is happening, right? So this is not, and if you backtrack that, everything is moving towards you here, but the same thing is happening here. If you're standing here and you think everything's moving towards you, you think you're at the center of the universe. But if you stand here and the same thing is happening, you think you're at the center of the universe here, right? There is no center because the universe itself is either getting bigger with time, or if you backtrack in time, everything is getting closer together. So there is no center. It's just expanding, or reverse time, it's contracting. Right.
And I think the hard thing is that we're stuck in, 2 or 3 dimensional thinking where we're almost kind of being pushed. We're moving and we're not really moving. The space between us is expanding, and it's expanding everywhere. So again, we have to think in that additional axis of geometry.
So actually, let me give you this analogy though too. So if we break it down from 3-dimensional space to 2-dimensional space, right? And the analogy that everybody uses is drawing polka dots on a balloon and inflating the balloon, right? And that's the analogy for the expansion of the universe. So no matter what polka dot you're on in that balloon, when you look at the other polka dots, they're all moving away from you, right? And so there is no center to that surface of the balloon, right? And that's not a perfect analogy because there is a center to the balloon, right? But if you're stuck to the surface of the balloon and that's all that exists, right? There is no center to that. It's just a continuous, basically, surface that either gets bigger or gets smaller. And there is no center to that surface. Yeah.
Well, now that our minds have been completely blown, we're going to take about a 5-minute break just to hit a reset. And want to invite folks on Zoom to stay tuned. We'll be doing some club business, but just want to thank Patrick for a great presentation. So how about a round of applause?
Thank you. Thank you.
Thank you very much.